All right, let me talk about our first results of DOSUE-RR experiment. So this is a search for dark photon, dark matter in the mass range at 74 to 110 microelectron volt. So I'm Osamu Tajima from Kyoto University on behalf of the DOSUE-RR collaboration. So let me briefly mention about the first dark photon, dark matter. Maybe you know very well. So electromagnetic fields of dark photon, dark matter appear via kinetic mixing. So that's why we can characterize a dark photon by using two parameters. One is coupling constant, kinetic mixing chi, and another one is dark photon mass itself. So suppose we have a boundary of electromagnetic field, such as metal plate. Because of the boundary condition at the surface like this, and the conversion photon is almost perpendicularly emitted from the boundary. The principle to search for dark photon, dark matter is detecting this conversion photon. So for the case of radio range, as you know, so we picked up this conversion photon by using a horn antenna. Then after the amplification, we measure the frequency spectrum by using a spectrometer, such as signal analyzers. So this is just simulation results. So, if we have a signal, so we should observe such kind of sharp peak signal. And here, the peak frequency corresponds to the mass because dark matter is non-relativistic. And for example, 24 gigahertz corresponds to the 100 microelectron volt. And here, more important thing is peak height corresponds to the coupling constant. So maybe as you know, this is a constraint to date and in around the millimeter wave range. So here, for wide range, cosmological observation such as CMB, cosmic microwave background observation gave such kind of wide constraint in wide range. And for the infrared and the far infrared range, and solar lifetime give indirect constraints like this. And below the 10 gigahertz for the conversion photon, the many action experiments give strong constraints here. However, if we look at this millimeter wave range, so there is no strong constraint here, while there are motivations from the string theories and inflation models, as you know. So that's why we aim for exploring this wide range. So the DOSUE-RR is series of experiments to explore this region. All right. So this is a DOSUE-RR collaboration. DOSUE-RR means dark photon, dark matter observing system for unexplored radio range. Since most of the collaborators come from Kyoto University, so we hire the local women's phrase in Kyoto, DOSUE. So we use this phrase, we named our collaboration name like this. Okay, so let me briefly discuss about what is a measure noise source. So if we assume such a coupling constant and the effective aperture area for the horn antenna, and also we assume a standard assumption, for example, density of dark matter like this, then for that case, conversion photon is 10 to minus 19 watt level. So this is faint. So suppose if this horn antenna picked up the thermal radiation from the ambient. So for that case, roughly speaking, the intensity of this noise, thermal noise is 10 to minus 17 watt level. So this is comparing to the conversion photon signal. So this is really high. So that's why our strategy is maintenance the system and also the optical path from the converter in the cryogenic shield around the 3 Kelvin. So based on this effort, also we can suppress the thermal noise from the outside. So this is actually the same strategy as the recent CMB experiments. All right. So this is our instrument's photo. So this is a cryostat. So inside of the cryostat, we have 30K shell and 3K shell. And in the 3K shell, we have horn antenna. And after the amplification of cold low noise amplifier CLNA, then amplified by warm WLNA, we measure the frequency spectrum by using a signal analyzer. So based on such kind of cryogenic concept, we success to achieve the lower system noise comparing to the ambient system case. So this is more photo. So this is a horn antenna to be set in the 3K temperature. And we actually set the CLNA inside of the cold box because we want to avoid the thermal radiation from the CLNA coming into the horn antenna. So that's why we put the cover here. So this guy is actually the student in Kyoto University. And the design of the system and the construction of the system and performing the explanation is his master thesis research, actually. Okay, for the calibration. So as you know, the low signal, measured signal is amplified by the LNAs. So input signal is amplified by the gain factor, and also we have a noise offset like this. So that's why we have to calibrate the gain. So for the gain calibration, so instead of the conversion plate, we set the black body sources. And we use two different temperatures. One is maintained in the room temperature black body source, and another one is a liquid nitrogen temperature black body source. And by using these two different black body sources, we calibrate the gain, and the typical gain is about plus 62 dB level. And also we measure the time variation, and the typical time variation in our scale is much, much less than 1%. And for the dark photon search, so one calibration for the effective aperture area is also important. So this is because effective aperture area of horn antenna is smaller than the physical area. So this is because there is a finite beam resolution. So that's why by using exactly same horn antenna and also the artificial source, we measure the beam width as a function of frequency. So, so we obtain the consistent results as expected by the simulation, and we obtain the effective aperture area like this. All right. So for the search for dark photon dark matter, so we explored in the range of 18 gigahertz to 26.5 gigahertz for the conversion photon. And so these frequencies are actually limited by waveguide cutoff and the capability of signal analyzers. And for the signal analyzer, the bandwidth of single FFT scan is actually limited at around 2 megahertz, comparing to the whole range. So this is very narrow range. So that's why we swept this single shot from left to right like this. And we took 12 days to explore a whole range. And also, every 100 megahertz interval, roughly speaking, every 40 minutes interval, we perform the gain calibration. So this is one example for the measured data power as a function of frequency around 18 gigahertz. And from this data, so from the fluctuation of the signal power, so we can intuitively imagine that our statistical error level is slightly below the 10 to minus 19 watts level because of the accumulation of the data, statistics, I mean. So which means our expected sensitivity we achieved is 10 to minus 10 for the chi. And from this power spectrum, so we extract the dark photon power by using by the fitting. So we assume that this fit function, the signal shape with multiplied power, and also background. So for the signal, we assume just a standard assumption. So if we give a frequency nu 0, for that case, so we should see such a signal. And for the background, we simply assume the one order of polynomial. So for each frequency, we extract the power. So this is a results of the signal extraction. So extracted power as a function of frequency from 18 gigahertz up to 26.5 gigahertz. So from this plot, so you can understand. So this is very consistent, and there is no significant excess at the specific frequency. And if we calculate the p-local, I mean null signal hypothesis, for that case, for some frequency range, so we obtain the small number. However, taking into account the look elsewhere effect among all more than 4 million fit results, the global p-value under null hypothesis is only 68%. So which means, so there is, in this data set, we found no significant signal. So even though we obtain such a large p global number, so if we look at the fit results, for example, this region, so we wondered, this is really no discovery or not. So that's why we additionally accumulate the data, and then we confirmed, okay, there is no signal, unfortunately. And we did the same thing for other frequency region like that, and we confirmed zero consistent results. All right, so this is a systematic errors for the chi. So total systematic error is 7%, and most of them come from the uncertainty, actually, the precision of calibration, and also the model uncertainty for the dark matter density. Okay. So this is our upper limits at 95% confidence level from this work. So our constraint is like that. And again, so this is our first exploration in this mass range. And this is the most stringent constraint to date. And also, this is tighter than the cosmological constraints. Okay, so let me summarize my talk. So this is I talk about the first results of DOSUE-RR, and we searched for the dark photon dark matter using a cryogenic, I mean a low thermal noise millimeter wave system, and we found no signal in this mass range, and we set the stringent upper limits to date. And so if you are interested in more details, so our paper is already available on archive, so please take a look at it. And actually, this is my last slide. So I said, so DOSUE-RR is series of experiments, and this is our first results. And right now, we are preparing a low frequency setup and high frequency setup. So please stay tuned for our hopefully near future results. Yeah.
All right. Cheers. Okay. Thank you very much, Osamu. I'm sure there are questions. Let's start here.
Thank you very much for this very nice talk. I was a bit surprised on slide 9. It seemed like your conversion plate is at room temperature. Is that because it's making the calibration easier because you can replace it with the absorbers? Or is that the only reason, or why do you do it like this? It seems like if you move it inside the cryostat and close off everything, you might have a lower noise temperature and shield yourself better from RFI.
This is because, you know, the whole antenna has a sensitivity for like this direction. So we just cut the thermal radiation from the
yeah, but my question is, why is your aluminum plate that you use as conversion plate, why is it at room temperature and why not inside the cryostat?
Yeah. The main reason we put aluminum plate outside of the cryostat is to perform the calibration easily.
I see.
So that's the reason. Of course, if we put the aluminum plate inside, the sensitivity will be better. But so for that case, maybe calibration will be difficult.
Okay, yeah, let's
so
discuss
for the initial step, so we prefer to perform the calibration easily.
Yeah, okay, that makes sense. Thank you.
Okay.
You have built a very nice total power radiometer in your setup, but I think you could gain significantly when you either convert it to a Dicker radiometer where you may not like the switching noise, or to what is less well known, a correlation radiometer where you even gain sensitivity. If you like, we can discuss it during lunch.
Sorry, I don't understand your question. Please say again.
What your setup is essentially a total power radiometer.
Right.
And we all know about the way to measure with higher sensitivity, which is a Dicker radiometer, which has, however, a switch, and the switch may produce some noise in some cases. And the even better way is a correlation radiometer, which is less well known and gives you another factor 2 in sensitivity and has no switching noise.
So you mean if we employ a switching scheme?
We discuss maybe during lunch.
So let's thank